let me first start with some administration. So actually, some of you noticed that the PSAT problem number 2B, there's a slight problem. I posted a comment about this in the website, and I'm going to, so there's an assumption I want you to make for problem 2B. Just look at the website and the announcement. If you have any questions, come to me. Okay, so that's one thing. The other thing is next week is Thanksgiving, so happy Thanksgiving. And the week after, I'm actually away giving some keynote talk, but we're gonna actually, it works out really well because the topic of that lecture is gonna be about what's called BARGs, or batch arguments. That would lead us kind of in the final class to get kind of our snarks that we were kind of, building for. And that lecture covers a work by three authors, Jane, Jin, Kudhurti, Jane, and Jin. And Jane Jin is going to come here and present the results. So you'll get the author kind of presenting the relevant work. And then the final class will kind of wrap everything up and show you how to get kind of what we worked for this entire semester. Okay, so just kind of what we're going to focus on for today. So any questions about administration, about questions from last class, anything before we kind of go into the material? Yeah?
So when doing the homework, I realized that one thing, I'm not sure if that's like something you change with GKR, but GKR only has like the add and the multi gates, right? But is there any way to get subtraction to work?
So let's come to me after class, okay? Okay. Okay, any other questions? We'll talk about this after class. Okay, so what's the plan for today, or where we kind of left off last class and where we're heading for today? So last class we defined kind of the Fiat-Shamir paradigm. So kind of from the beginning, what did we do? We showed kind of this kind of interactive protocols, and then we showed like, for example, GKR, which is only for bounded depth computations. Then we showed you can build from that a PCP, and then use that PCP to kind of shrink it using cryptography and get actually 4-message, that was the Killian-Mikali protocol, 4-message protocol proofs or arguments, computationally sound proofs, for all of NP where it's very succinct. Okay, so you can kind of take any witness for NP, and instead of sending this witness, which is long, I don't know, poly n bits, I'm going to shrink it to kind of via an interactive protocols of 4 messages to get it kind of, the number of bits is proportional to the security parameter, which can be much, much smaller. So that's what we showed. That was the Killian-Mikali protocol, but that was 4 messages. So now we're kind of towards the home stretch. We want to kind of get around these 4 messages and reduce it down to just 1 message. So how do we do that? So last class we defined this paradigm called the Fiat-Shamir paradigm. It was introduced exactly for this purpose, to kind of eliminate interaction from interactive protocols. So by essentially replacing the verifier with a hash function. And now there was a question. It's a very nice, very simple, very efficient kind of paradigm, very elegant in my opinion. But then there's a question, is it sound? If you start with an interactive protocol that you can prove soundness, when you apply the Fiat-Shamir paradigm, is the protocol or the proof still sound? That's the question. And what we proved for this protocol, Killian-Mikali protocol, is it is sound if you apply the Fiat-Shamir paradigm, but if this hash function is kind of what's like, is a random oracle. So instead of being actually an explicit kind of circuit, if we think of it as a completely random function that both parties have oracle access to, then it's sound. But in real world, there's no kind of random oracles in the sky that all parties have access to. We actually use specific circuits to replace this hash function. And then there was kind of this question of when we actually use the Fiat-Shamir paradigm with a specific circuit, with a specific hash that's computable by a specific kind of circuit, is it sound? Okay, and that was kind of open for a long time. It was a very, very important open problem because Fiat-Shamir is used all over the place in practice. So kind of understanding whether it's secure or not is very important. And we could only analyze it in the random oracle model. So now not in real world settings. And as I pointed out last time, the random oracle model actually worked out to be a very good proxy. So none of the schemes in practice actually that we proved security in the random oracle model turned out to be broken. So turns out it's a very, very good proxy for security. But still kind of, at least for me as a theoretician, I want to understand kind of why, you know, when we replace it with an actual function, an actual program, why is it secure? So, and frankly, I still don't understand why it's such a good proxy, I have to say. It's still kind of, it's surprising to me that never, ever we had, like it's really, really kind of approximates, you know, security in, to very well, even though, as I mentioned, we do have counterexamples. We do have examples, contrived, not real-world examples, but contrived examples, where the protocol are secure in the random oracle model and not secure in, you know, when applied Fiat-Shamir. And actually, interestingly, Kili and Mikali is one of them. It's actually one of the protocols where actually it was proven that if you use a certain hash function, collision resistant, but a certain hash function, then actually you can prove security. If no matter which specific function you use for the Fiat-Shamir, it will for the Fiat-Shamir function, it will not be secure. But this specific hash function, which is collision resistant, is contrived. So we still don't have kind of real world natural application of where security was proven in the random oracle model, but turned out to be false in the real world. Okay, so kind of that's where we're heading to, okay, trying to prove the security of, or the soundness of the Fiat-Shamir paradigm. And kind of along the way, what we did is I defined a certain protocol, which is zero knowledge. So we kind of took a detour, talked about zero knowledge, and we looked at a specific protocol, zero knowledge protocol for graph, for hamiltonicity, for whether a graph has a Hamiltonian cycle or not. That's an NP-complete problem. And so here's just a recap, because we'll look at it again today. So here's a proof, a three-message proof system. The prover is trying to prove to the verifier that a graph G has a Hamiltonian cycle. And we want to do it in zero knowledge, so in a proof that gives no information. And the way we did it, we said, okay, the prover has a Hamiltonian cycle. He does not want to reveal any information about this Hamiltonian cycle to the verifier. What would the prover do? He will choose a random permutation pi. He will commit, kind of put in a safe, a locked safe, only the Hamiltonian cycle of pi of G. So if C is the kind of the path, the Hamiltonian cycle in G, he will compute pi of the cycle. Okay, so the cycle inside pi of G. And then he's going to get a random bit, and he's going to give an answer. What is the answer? If the bit is 0, he's just going to open the cycle. Hi. He's just going to open the cycle. Okay, so, or maybe I should say like pi of C. So he's going to open only the places where there's a cycle, and the guy's going to check that, yes, it's an indeed cycle. Okay, but we need to make sure that the cycle has something to do with the graph itself. So if the B is 1, then we check that indeed that you give the permutation, you do not give the permuted cycle, otherwise it will give information. So you only give the permutation, and you open only non-edges in pi of G. So now you know everywhere in pi of G that there's no edge. In this commitment, there's no edges. Okay, so again, let me just emphasize to recap. This commitment, it's committing to n, if n is the number of nodes in the graph, it's committing to n squared values, where there's a 1 if there's an edge, 0 if there's not an edge. Okay, for any ij, it says 0 or 1, whether it's an edge or not an edge. And if b equals 0, we only open kind of the places where there's a Hamiltonian cycle. We check that everything there should be 1, and you check that it kind of closes, that it corresponds to a cycle. And if b equals 1, you give the entire permutation, and you open the non-edges. Okay, and now the claim was that this is indeed zero knowledge, and the intuition was, well, if you open 0, he doesn't learn anything, because it just gets a random cycle, has nothing to do with the graph. Just any random cycle, that's what he sees. Okay, he could have generated, it's no information about the graph. And if he gets b equals 1, then what does he see? A random permutation and a bunch of openings of 0. That's no information. And as we said, the soundness here is only half. That's the problem. Probability half you can cheat, because if you guessed a cheating prover, I can guess B, and if I guess B correct, if I guess B, I can at least cheat on that B. So I can always kind of, even if G doesn't have a Hamiltonian cycle, I can always answer correctly on one of them, but not both. So if I guess your B, I can cheat you. So this gives only soundness half. Okay, this is just a recap, and that was kind of, I motivated this kind of show that this is not even secure in the random oracle model. So actually, to get security, even in the random oracle model, you need to repeat in parallel. So today we're going to, when I say now PV, like this, so when I say like the protocol PV, let me think of, I want you to, throughout this class, let's think of it as parallel repetition of this. With like security parameter lambda copies. Okay, so now, I mean, soundness half is really not good for us. That's not what we want. So think of it that we repeat this in parallel, security parameter number of times. Okay, so in other words, the prover, lambda number of times, each time chooses a fresh permutation pi. Commits. So he does this lambda times each time with a new permutation pi. This is very important. And people see why it's important that the permutation is fresh each time. If you use the same permutation and you open B0, B1, you learn everything. So each time you give a fresh kind of random permutation, you send in lambda times, you get a B for each one, and now you send a message for each one. Okay? So that was the protocol. Now we proved that it's secure in the random oracle model. Actually, we proved that any constant round protocol that has negligible soundness is secure in the random oracle model. We showed that last time. So it's secure in the random oracle model. And now there's the question, okay, is it secure in the standard model when we use Fiat-Shamir? And what we're going to show today is yes, it is secure. So that's kind of the first thing. We're going to show that this protocol P and V, and again, when I say P and V throughout today's class, it's a parallel repeated version, okay? So we're going to show that P and V are secure when you apply Fiat-Shamir in the standard model, okay? For some commitment, not every commitment. So we'll open this box a little bit and show that there exists a very natural commitment scheme, that with that commitment scheme, we can argue that this is secure when the hash function, we'll actually construct a hash function. I'll give you an exact hash function and say, if you use this hash function for the Fiat-Shamir, you'll get security or soundness. Okay, but this hash function, to argue, you'll need to assume something about the hash function. I mean, this hash function assumes some cryptography, and the cryptography it assumes is the existence of a fully homomorphic encryption. I'll define what that is, but not just a fully homomorphic encryption, we'll assume also that it's circular secure fully homomorphic encryption. I'll define what that is as well. I just want to say, actually, today, we don't need the circular secure version. We know how to get rid of it. But what I'm going to explain today does use this version. It's just simpler. Okay? And this can be, we believe this is true. There's instantiation based on circular secure learning with AIR, LWE. But we don't need to get into these details. Okay, so that's what we're going to do in the first part of the class. And the second part of the class, so now you can say, okay, let's say we prove Fiat-Shamir. Why am I obsessed with this protocol? And let's say we prove Fiat-Shamir for this protocol. So what? Like, why is that? Why should you be engaged? So let me try to give you motivation for you to stay awake and listen to me. So why is it? So this protocol in particular is very important. Why? So what I'm going to show is when you apply Fiat-Shamir to this protocol, you get what's called a non-interactive zero-knowledge proof, NIZIC for short. So once we do that for this protocol, because it was zero knowledge, we can argue that when you apply Fiat-Shamir, you get non-interactive zero knowledge. And to get non-interactive zero knowledge based on lattices was an open question for a very, very long time. And this was resolved in this paper that I'm going to present, in this work that I'm going to present to you by Canetti, Lombardi, and Wicks. So kind of one of the motivating examples is that we get this non-interactive zero knowledge. That's one. But the other motivating example is that actually this technique is much more general. Okay, the technique of Fiat-Shamir that I'm going to show you is much more general than just for this protocol. Actually, it's a very general technique that can be used for many protocols. And in particular, we used it later, this exact technique, and I'm going to try to show you how it can be used to get to show that the GKR protocol that we studied in the beginning actually is secure in the standard model. When you apply Fiat-Shamir to it, you get security under learning with error, or FHE. Again, as I mentioned, this circle of security can be prevented. I'm just showing you the result that uses it for simplicity. Okay, so it's not just for this protocol to get NIST, you can actually use it to get SNARGs. And moreover, what you'll see after Thanksgiving that Zheng Zhong is going to present, he's going to use this exact same tool to get batch arguments for NP. So this kind of Fiat-Shamir is baked into all our results, almost. Okay, so it's actually very general and nice. Yes?
How does that relate to, because last time we went a little bit over the result of Weisbach about the fact that you can have
Great question. Great question. Okay, let me repeat your question because you have a great question. So last time I kind of showed you that there's actually a tension. If you have an interactive proof that is zero knowledge, then I kind of gave you this high-level intuition that if it is really zero knowledge, you cannot apply Fiat-Shamir to it. It will fail. And here I'm saying, oh, we're going to apply Fiat-Shamir to it, and not only that, we're going to get zero knowledge, non-interactive zero knowledge. It's like, wait. Last time, you said you can't get zero knowledge. Now you're saying this. I'm kind of contradicting myself here. Okay? So again, let me repeat it just to make sure we're all on board. Last time I said a protocol that is zero knowledge cannot be Fiat-Shamir secure. Now I'm saying, guess what? This protocol is Fiat-Shamir secure. Okay, so first of all, indeed, I have no reason to believe that this protocol is, when you repeat it in parallel, that it's zero knowledge. We know that it's zero knowledge if in the probability without parallel repetition. We know that it's zero knowledge if you repeat it sequentially. If you repeat it in parallel, we don't know that it's zero knowledge anymore. That's first. Second, so now you're saying, that next thing you can say is, oh, so now we know that it's not zero knowledge. Almost. Actually, the result does show that parallel repetition does not preserve zero knowledge. But actually, it's not going to be completely because I'm going to change the commitment in a way that you'll see in a minute. So not quite. But then you can say, okay, but how do you get Nizik out of it? How do you get it seems completely opposite because I just said Fiat-Shamir is in contradictory of zero knowledge. And now I'm saying you apply Fiat-Shamir and you get zero knowledge. Okay. So what we get is non-interactive zero knowledge. And non-interactive zero knowledge, the simulator, I didn't define what it is, so it's hard I'll explain it as I go. But the simulator has more power than the cheating prover. Remember, the reason I said that if you have a zero knowledge protocol, why can't you apply Fiat-Shamir? Because we said, look, the verifier a cheating verifier can use the Fiat-Shamir function. He can behave maliciously. He's behaving with the Fiat-Shamir function. Now, you should be able to simulate the view. So if you have an efficient simulator that simulates the view for X in the language, he's an efficient simulator. He doesn't know which instances are in the language or outside the language. It's NP, it's hard languages. So he probably will succeed in simulating the view of instances outside the language. Otherwise, he's like a P, he's a kind of distinguisher. You can use him to show that the language is in P, not in NP. So and that's why there cannot be a simulator. Because the simulator, he can act like a cheating prover. In the non-interactive setting, he cannot, because we're giving the simulator extra power to choose the common reference string. We'll talk about it when we get there. But it's a model that's a little different. So actually, I'm going to talk about this more in length when I get there. But since you asked, I wanted to give a preview. So indeed, there's tension, and we'll see how to overcome it. It's actually really interesting that kind of, that it's a belief that you can't use Fiat-Shamir once zero knowledge is kind of in contradiction to Fiat-Shamir, but actually we use Fiat-Shamir to get the non-interactive version of zero knowledge. But we'll go into detail when we get there. Great question. Any other questions? So my plan next is to prove the soundness of this protocol, the parallel repeated version under Fiat-Shamir. But any question before we go there? Okay, so the result. So as I said, this is a result of Canetti, Lombardi, and Weeks from 2019. It's so beautiful and simple. So this was an open question for a very long time. And I want to give it to you as a kind of evidence or an example of something that we thought was so hard. And then if you just think about it like a little differently, you twist a little bit, it's so easy. So I'm going to have you guys try to come up with a proof, okay, of this. So let's try to do it interactively. And I want you to prove to me that this protocol PV, but think of it again, repeated in parallel, is sound. Okay. So I'm going to give you a few hints and we'll get there together. Okay. So one thing that's really nice about this protocol is, I want to argue, okay. Let's recall, what is the Fiat-Shamir paradigm? The Fiat-Shamir paradigm says that, we choose some hash function, some hash key from, there's some Fiat-Shamir hash function that generates a hash key. And now we want to say, let me denote, for simplicity, these messages by alpha, beta, and gamma, okay? Even for now, let's even not think of this specific protocol. Okay, let's think of just a protocol. The prover sends alpha, verifier sends beta, prover sends gamma. Okay, let's not even go into the specific details. I want to prove to come up with a hash function. So I want to come up with a hash function H, which, generates a key for a hash and then evaluates. That's just a hash function, such that this remains sound. Okay, so I have this, there's some NP language X. I want to prove whether it's in the language or not. This is my proof system. And I want to find a hash function for which is sound. So what does this, at first it seems like it should be very easy. Why should it be very easy? Look, take, let's say, X not in the language. We need to focus on X not in the language. X in the language, it's complete, like completeness, that's easy. I want to argue you cannot cheat. Okay, so now, what do I need to say? I want to say, I want that for any X in the language, so fix one X in the language. I want to argue that you cannot find an alpha and beta, which is H of alpha, and the gamma that's accepting. But now, this is a proof system. So every alpha has very few betas for which there even exists a gamma that's accepting. Right? So again, because it's fixed X in the language, first thing we notice, just by definition of a proof, that for every alpha, any possible alpha, there exists very few betas for which there exists an accepting answer. So there exists very few betas such that there exists gamma for which alpha, beta, gamma are accepted. Okay, so that's the first thing we notice. Because it's a proof system, by the virtue of a proof system, for every alpha, there are very, very few. Actually, note in this protocol specifically, there's one. Because if the graph G does not have a Hamiltonian cycle, take a cheating prover that sends alpha. Alpha is a bunch of commitments. Now, let's actually, in each commitment, look, either they're sitting a Hamiltonian cycle or not. You can't answer both questions. We know that. If you can answer both questions, well, it won't be sound. So you can only answer one question, and each one can only answer one. So this protocol, it's even for this specific protocol, let's assume even, let's even assume what any proof tells you is that for every alpha there exists a few. But let's for simplicity, because that's the protocol we're dealing with, let's suppose there exists a unique, this is a symbol for unique, by the way. There exists a unique beta that can be extended. Now, all we need to do is not hit that beta. So all we need, think about it, it seems so easy. All we need is to find a hash H, like a hash key, such that eval of hash key in alpha is not equal. So let me call, for every alpha there exists a single beta. Let me call it beta bad. Like that's the beta we want to avoid. Okay, so for every alpha, there exists a single, it's a beta bad of alpha. It's a function of alpha. For every alpha, for every commitment, there's a different, either you can answer 0 or 1. So for any alpha, there exists one challenge, beta, for which the prover can cheat. Now the cheating prover wants to hit that bad beta, because that's what he can cheat on. Our job of protecting this is to make sure that every alpha does not equal to this beta bad. But how hard can it be? We just want to avoid one. You know what? Let me give a suggestion. Eval hash key, or here, h of alpha equals beta bad of alpha plus 1. It's not beta bad. I avoid the bad one. I'm going to use this for my hash function. Anybody see a problem with this? Yeah?
Well, it's not really unique beta because you're kind of using the computation assumption for the commitments.
No, actually, I'm using the computation. Okay, good. So what was said? Well, actually, it's not unique because the commitment here has a computational assumption. But actually, this commitment will be statistically binding. So it's only the hiding is the zero knowledge is computational. But actually, you can open it. Suppose there's really like you're binded. Okay, you can really only open it in one. Like you can't open it 2 different ways.
But still, the feature core principle is going to be many permutations for one.
That's fine. That's fine. But you're right. There's many permutations. But suppose you can open to both, then you can give me both this message and this message. If you give me both this and both this, it means that you have to have, this G must have a cycle. Because I know that there's a cycle, and guess what? It's not in the non-edges. So the cycle has to be in the edges. So you cannot really, you can open only one. Okay, so again, all I want, it seems like so easy. I have a proof system. For every alpha, actually the prover can only cheat on one single beta. All I want to do is avoid that beta. So okay, I'll give just avoid that. Do beta plus 1. This is delicate. Anybody see why this doesn't work? Yeah?
Don't you have to open the commitment to find out which is the bad beta?
Exactly. The problem is computing beta bad is really hard. How do you know what beta bad? For example, so computing this is hard. Actually, if it were easy, you wouldn't need interaction at all. It would be NP. You'd have a succinct witness for NP. You just give alpha, you compute this is the beta, and then you give gamma, and everything's information theoretic. The problem is computing. The power of this thing lies in the power of this interaction lies in the fact that computing what the bad beta is hard. Here, for example, how do you know which beta you can cheat on? Well, if you open the commitment, then you see, okay, is there, is there a lot of ones? Is it only a cycle? But you need to open this commitment. So computing this beta is hard without additional information. Okay, so now what do we do? So we can't give that as a hash function because this is a hard computation. Okay. So here's the first kind of, so there are a few aha moments in this paper. The first one is, you know what? Maybe if this commitment had some trapdoor, maybe, there's some trapdoor information that with the trapdoor it becomes easy. So then let's do that. Let's use trapdoor in our hash function. Okay, so now 2 things I'm going to do next. First, show you how you construct a commitment with a trapdoor. That will also be useful here, so it's going to kind of be a stepping stone. So I'll show you a specific commitment, which is what we use, which has a trapdoor. to make beta easy. And then we're going to deal with the next issue that comes up, which kind of the next aha moment appears in, which is, well, you can't use this trapdoor in the clear because if you just, you can't give the cheating prover, you can't give the cheating people like the trapdoor. Actually, the problem will not be the cheating prover. The problem, if you give the trapdoor, it's not zero knowledge anymore. So this trapdoor needs to stay hidden. You can't just use it. Like the reason it's a commitment, it has a purpose. We don't put things in the clear for a reason. So we'll first see you can make it efficient given the trapdoor, and then we'll show how this, nevertheless, even though we need to keep this trapdoor secret, the mere fact that it exists can be useful for us to do the Fiat-Shamir. Okay? Questions? Let me remind you that I really like questions. Good, bad, all of them. They're all fantastic. Yeah?
I'm just curious, is there like the common random string commit you use in the second step where you want to make the trapdoor somehow random enough that it's not known?
So the common random string will be used in many places. The first place it's going to be used is even to make sure my commitment has a trapdoor. So, and then it's going to be used again and again. It's going to be used all over the place. So we'll see that next. So any other questions before we proceed? Okay, so step one, let me just tell you how to construct the commitment so that it has a trapdoor. And the way I'm going to do it is just using encryption scheme. Okay, so let me define the notion of public key encryption. And did we define public key encryption last time? No, right? Okay. So let me define the notion of encryption, and we'll use that as our commitment scheme. Okay? So what is an encryption? So a public key encryption with a message space. There's a message space associated with it. And these are the messages that we're going to encrypt. It consists of 3 algorithms. So one is gen, it has its own key generation, not to be confused with a hash function that generates hash key. This generates public key and secret key. So this just generates a pair of public key and a secret key. Let me just mention 3 PPT algorithms. So we have probabilistic polynomial time algorithms. The first just generates 2 keys, a public key and a secret key. The encryption algorithm takes as input a public key and a message from the message space, and it generates a ciphertext, okay, from a ciphertext space. And the third algorithm decrypts. So it takes a secret key and a ciphertext, and it generates a message in the message space or like bot. Namely, I failed. I tried to decrypt, but I failed. Okay, and the properties we want, the first is correctness or completeness, which just says if you encrypt a message and then you decrypt it, you get your message back. Okay, so it just says for every m, for any message, the probability that you decrypt, so the probability is over a sample, secret key and public key and secret key from keygen. And then use the secret key to decrypt an encryption of n. So it says, if you encrypt n, you generate a pair of keys. You encrypt the message m, and then you decrypt it. You get back the message with probability 1. Okay, that's just correctness. What do you expect? If you take a message, you encrypt it, and then you decrypt it, you should get the message back. The important property then is security, or what's called semantic security. And this says that any 2 messages if you encrypt one or encrypt the other, can't distinguish between the two. They look the same. They're computationally indistinguishable. So it just says for every M0 and M1 in the message space. So typically we think, by the way, the length of M is revealed. Typically we think of the message space as having fixed size. For us throughout this entire lecture, and often is the case, we can think of M as just containing two messages, the 0 message or the 1 message. And if you want to encrypt longer message, you just encrypt bit by bit by bit. That's a common way to do encryption. Not in practice, but in theory. In practice, it's often not fast enough, but in theory, you can just encrypt each bit separately. But in general, for any two messages in the message space, if it's just 0 ones, then for the message 0 and for the message 1, the claim is that if you generate public key according to Gen and encrypt M0, this is indistinguishable, computationally indistinguishable from generating a public key according to Gen and encrypting message 1. So for any messages, you know the messages I encrypt. I'm telling you, I'm encrypting M0 or M1. You can't tell the difference. I'm giving you, you don't know, I'm giving you one of them, you have no idea if it's M0 encrypted or M1 encrypted. Okay, note, there's no randomness over the messages. For any two messages, fixed messages. You don't know if I encrypt, yeah, so even you don't know if I encrypt, and if I give you two encryptions of 0 or I give you an encryption of 0, 1, can't tell the difference. Okay? So that's the definition, and we have these public key encryption schemes under a whole slew of assumptions, lattice-based assumption, not lattice-based, like a discrete log that we saw earlier in the semester, and so on. But I don't want to talk about instantiation because this is more kind of class on proof systems, and I don't want to make it too hardcore crypto. So let me just use this, not show how to actually construct this, but we have many instantiation constructions. But suppose we have this, let me show you what the commitment would be. So now what I want the commitment to be, instead of commitment, make this an encryption. Let me actually put another color. So make this be an encryption with some public key of pi. So what I'm telling the prover now, I'm telling him, look, I want to be able, in the analysis at least, to open up there and see kind of where the ones are and where the 0 ones, so that later I'll be able to understand where the non-edges are, and so what's the bad beta. So now I want to tell the prover, so please don't, the commitment I want you to send me is the encryption. Now it's hiding, it's still hiding, yeah, nobody, it's still 0 knowledge, it still satisfies kind of, it's locked, it's like the verifier has no idea what's in there. And supposedly, it's still binding because you know, once you encrypt, you're stuck. It's like the message is sitting there because then you can use a secret key to decrypt it. So it really has the hiding and binding property. Great, it's like a real commitment scheme. Yeah? Yeah.
Does public key encryption imply that there's no possibility of a second secret key that decrypts it to something else?
Okay, great question, great question. So great. So you're asking, wait, what if the public key has many secret keys associated with it, and one of them decrypts to M and the other one decrypts to M prime, let's say. So no, here I say no. By my definition, no, because my correctness says that if you choose public key and secret key pair, with probability 1, you will always get your message back. So there's no secret key that will give you a different message. That's my definition. So what you're proposing is not, for me, it's not doesn't satisfy my definition. So now use a public encryption that satisfies my definition. So now you're binded. Good, great question. These are really, really great questions. Yeah?
Here in the probability expression, you're choosing public key and secret key to all come from the same Gen function.
Yeah.
But what if like another, like, it doesn't guarantee anything about like a different.
Okay, very, very good question. Very good question. So so the point was the following. Look, we have all these guarantees. The correctness and the security, assuming the public key is generated according to gen. Now, my question here, who generates this public key? How do I know it's generated according to gen? If we let the prover generate the public key, he then maybe it's a bad public key that is never going to appear here. And for that bad public key, maybe your concern is valid. Maybe you can open it in different ways. And you're completely right. That is a problem. Actually, even in it's not a hypothetical problem. Our scheme that we use, that we want to get the central lattice assumption, that specific scheme we use has that property, has that problem. That if the key is generated badly, actually there's no binding. I can cheat, I can open two different ways. I will never be able to do that if I generate according to gen. But if I generate it maliciously, I can choose a very bad public key. Nobody will be able to tell the difference. It will look like a good public key. But it's actually generated completely differently, and it would have never appeared in gen. And with that public key, there's no correctness, and I can cheat and I can do whatever I want. So very good. You found the problem in this approach. So what do we do? How do we fix it? So this comes to your question in the beginning. Well, you know what? Let's assume that there's a trusted party that generates this public key for us. So let's assume for now that there's kind of a common reference string. We all agree there's like a public key sitting here. That's in the kind of what's called a common reference string or a common random string. Everybody knows it, both the prover and the verifier. We all agree on this public key. And we assume that it was trusted, like generated according to gen. Nobody has the secret key. Okay, nobody has the secret key. We'll never need to open the secret key. So in this protocol, what do I do? I'm a prover. I encrypt bit by bit. So how do I encrypt? I use randomness. So I didn't say, but this encryption is a randomized protocol. So I choose randomness, I encrypt the bit. I choose randomness, I encrypt the next bit. I choose randomness, I encrypt the next bit, and so on and so forth. And when I'm asked to open, I reveal my randomness. So look how I encrypted. See, there's randomness. I took the encryption with public key and my bit 0 or 1 with this randomness, and see, that's what's written here. So I can just open without using secret key. Nobody knows the secret key. The secret key is gone. Someone just came up with the public key. And I open here now with the secret key, but I show you the randomness that I used to encrypt. And that kind of, is an opening for me. Yeah?
So does that mean your CRS can't be like a fully uniformly random string? Because if you were to read out the public key from that, you could also pull out the secret key?
So, okay, so the question was, great question. The question was, does that mean that the CRS here cannot be truly random? Because it's not truly random, it's a public key. A public key may not be truly random. And the answer is, well, first of all, some public key happen to be truly random. The public key for this scheme is not truly random. However, it's indistinguishable from being truly random. Now, so the scheme we actually use, the public key has the property. It's not random. It's like a LWE tuple for those who know what learning with air is. But that's not truly random. However, it is indistinguishable from random. Now, if you have soundness with public key that's indistinguishable from random, soundness should hold even if it's completely random. So actually, you can make this completely random. And actually, in the paper, they actually take advantage of that, because if the public key is completely random, then you get statistical zero knowledge, computational soundness, whereas if it's, you can play around with, in this protocol, especially when you go to the non-interactive version, there's a tension. You can either get statistical soundness and computational zero knowledge, or statistical zero knowledge and computational soundness. And you can play with this public key, whether to make it kind of the true public key, in which case you get statistical soundness and computational zero knowledge, or if you want to take like a fake public key, which is the all zero, and then you get computational soundness and statistical zero knowledge. So you can kind of play with these things. Okay, so this is the protocol for which we'll show that Fiat-Shamir holds. Okay, so again, the commitment is just replaced with a public key encryption. Yeah?
The common reference string, I mean the public key, by, for example, change the way of opening. For example, we also require the prover to provide the randomness for Gen.
Oh, that's a good, okay, I didn't, okay, good. So what you're saying, good suggestion. What you're saying is, you're saying, wait, how about he gives this public key, it can be malicious, but when he opens, we'll ask him, okay, so I'll tell you the problem with that. If when he opens, he gives the randomness he used, so you're saying, why don't he give the randomness he used to generate this public key, and now you know that it's a valid public key. That will indeed ensure soundness. However, that will break the zero knowledge. Because once you give the randomness, you also give the secret key away. Because this randomness was used to generate both of them. And if the secret key, then you lost the zero knowledge. But great suggestion. Okay, great, you guys, it's clear that you're thinking, which is fantastic. Great suggestions. Any other questions before we move on? Okay, so we're making progress. Now, what do we know? So let me hide this encryption for a second. Let's go back here. Now, okay, now I want you actually to forget that this was an encryption, because we'll use another encryption, okay? And I don't want you to be confused with this encryption and the other encryption. What I want you to remember about the commitment, that there's some trapdoor, like a secret key. I'll call it trapdoor on purpose because we'll have another encryption which will have a secret key. So what I want you to remember about this commitment is that there's some trapdoor information that with that trapdoor information you can open and know which B is bad. Okay, so a trapdoor has, a commitment has some trapdoor information. Okay, which allows you kind of to open it, in that case open the encryption, and then you know where the ones are, and that will help you decide where the bad B lies. Actually, no, I think I need to also add a commitment to pi there. Because otherwise how do you know which, maybe you can tell anyway. If you add a commitment to pi, it's easier, but if you don't add a commitment to pi, is it clear that just by seeing ones, it's easy to test yeah, I guess if you open both, you can see both. Yeah, I don't think you need it. Okay, but anyway, so good. Sorry. So now what I want to say, here's my hash function. It has trapdoor hardwired to it. Once he knows the trapdoor, this trapdoor depends on the public key and the kind of the CRS. It doesn't depend on the actual. Once he has the trapdoor, he'll know what the bad thing is, and done. Okay, it would be so. One can say, okay, use this as the Fiat-Shamir hash function. It's efficient, it's good. However, as we said, the problem is, then you know the trapdoor, it's sitting there, you know the trapdoor, and once you know the trapdoor, it's not zero knowledge. So that's the problem. And then there were attempts to try to do, okay, let's obfuscate these things, and a lot of kind of hammers were thrown in this direction, and it resulted in crazy assumptions. And anyway, there was a long kind of line of work where that's what we tried to do. Okay? But then here is their idea. So now I can tell you the next aha moment. So again, one option is to throw kind of what's called obfuscation at this. For those who don't know obfuscation, don't worry about it. Essentially garbling so that the trapdoor will be really hidden there. Nobody will be able to find it. And even that, it was like a messy approach that we tried, and we got really, really strong assumptions, which I have no idea if they're true or not. It was kind of a messy approach that a bunch of papers kind of followed that approach. Very complicated, and Okay, then came this paper. And here's here's the beautiful idea. Okay, so the beautiful idea was the following. They said, you know what? Yeah, you can't give trapdoor. That's a problem. Give an encryption of trapdoor. Forget about this encryption, right? That's a different encryption. So now fresh, new encryption. Why don't you give encryption? Let me denote the encryption of trapdoor here by hat. That's a common way we use fully homomorphic encryption, which I'm going to define next. So they said, put in the Fiat-Shamir hash function an encryption of the trapdoor that helps you open the commitment. I was like, so okay, and then what? What are we going to do with the ciphertext? We can't do anything with it. Ciphertext is like junk. What are we going to do with that? So their idea was, you know what? Don't just use any encryption. Use what's called a fully homomorphic encryption. What is a fully homomorphic encryption? I'll explain that next. But essentially what it does, it allows you to compute unencrypted data. Okay, so a fully homomorphic encryption is exactly the same as a encryption scheme. So a fully homomorphic, it's a public key encryption. So let me write a fully homomorphic public key encryption scheme is encryption scheme, gen encrypt and decrypt, but it also allows you to do computation on encrypted data. So what do I mean? There's an eval function. It takes a bunch of ciphertexts, and it can do computation on the bits hiding underneath the ciphertext. So it takes a public key, a description of a circuit, C, think of it with additions and multiplication, mod 2, and it gets a ciphertext, so encryption of B1, bit 1. Let me think of it now, as I said, think of it as the message space being 0 and 1. So it gets encryption of bits, let's say encryption, or I'll just call it ciphertext. Ciphertext 1 up to ciphertext n, each one encrypting a single bit. The circuit takes as input n bits and produces a bit, and it outputs some ciphertext. And this ciphertext, if here you have encryption of B1, B2 up to Bn, this ciphertext should have encryption of C of B1 up to Bn. Okay, so what this eval does, it gets encryption of bits, and it can kind of compute an encryption of the addition of the bits, an encryption of the multiplication of the bits, and so on and so forth. It can do arbitrary computation. It can compute an arbitrary circuit C. C goes from 0, 1 to the n to 0, 1. It can do arbitrary computation under the FHE. So I'll just write, maybe I'll write here, the completeness property for the eval. So I wrote the completeness property where all you do is decrypt. If you encrypt and decrypt, you get back the message. The eval also has a completeness property, which essentially says, so let me just write it down. So completeness of eval, I'll write it here. It says that for every B1 up to Bn, and the probability that when you decrypt eval, for every C, for every circuit C, when you decrypt, so choose a public key, secret key pair, when you decrypt, use the secret key to decrypt the eval function. So now evaluate with respect to the public key and the circuit C, evaluate on the n ciphertext corresponding to B1 up to Bn. So encryption, public key with B1, up to encryption of public key on bit Bn. So encrypt each of these bits. You'll get encryption of B1 up to encryption Bn. Then evaluate, do homomorphic computations on these encrypted bits with respect to circuit C. Now you get a ciphertext. You should get a ciphertext that encrypts C of B1 up to Bn. And indeed, the probability that when you decrypt, you get C of B1 up to Bn is 1 or close to 1. Okay? So again, what eval does, it does a computation on this encrypted data. It computes an arbitrary circuit C that when you decrypt it, indeed you get C with probability very, very close to 1. I wrote here 1 minus negligible as opposed to 1 is because our scheme has this negligible probability of error. So that's why I... Okay, so again, high level, what the FHE allows you to do, fully homomorphic encryption allows you to do, is to do this computation on encrypted data. So now the idea is, okay, questions about the fully homomorphic encryption? We're good? Yeah.
I guess does it matter what C is? Like, oh, never mind. Like, I was thinking just like arithmetic or.
Good. No, that's actually a very good question. It's a very good question. So the question was, this circuit C, what is it? So the circuit C, think of it as a circuit that has addition and multiplication gates mod 2. Okay? So any polynomial size circuit that has addition and multiplication gates mod 2. Great, thank you. Other questions? Okay, so now let's go back. So now we have an encryption scheme that we can do computation on encrypted data. Now let's go back. Remember, where are we? We're saying all we want is to avoid this bad. We want a hash function, its only purpose to avoid one single point. How hard can that be? I'll tell you, the hard problem is it needs to avoid the bad point for each and every alpha. That's kind of the hard part. That for every alpha you need to avoid the bad one. If you just wanted to avoid the bad one for one alpha, choose random. Probably you're not going to hit the bad one. But you need to avoid the bad one for each and every alpha. That's kind of harder. Okay, so now, but if we have the trapdoor, then it's easy. But we said, look, we can't give the trapdoor, that will break zero knowledge. So instead we say, you know what, let's give a homomorphic encryption of the trapdoor. Now, this seems like not helpful. Why is it not helpful? Okay, let's say you can compute on encrypted data. So, okay, do the computation of computing bad. So suppose you have, so now here's my hash function. It has trapdoor hardwire. So think of it like h of, instead of trapdoor, it'll have hat of trapdoor. Why not? And it will do this computation under the hood, like with eval, under the hood of the encryption. Very nice. So now on input alpha, you won't get the bad alpha plus 1, very nice, but encrypted. So why is that helpful? Yeah?
I think I guess the word solution, but you can also encrypt the eval, so that encryption, the ciphertext of two different messages are not equal.
Again, what are you saying? Encrypt?
Encrypt the eval h, the left-hand side of the equality, the eval hash key of a2 as well.
You can encrypt, exactly, that's kind of what, so, that's kind of what I'm doing. I'm saying this is this is a shorthand for, this is actually eval of, this is kind of the hash key. The hash key will have kind of trapdoor in it. And on input alpha, it should output this. And what we're doing, we're saying, okay, encrypt, or you can think of it, the hash key being trapdoor and encrypt the entire thing. You can do everything under the hood of the encryption. The problem is you'll get it. You want the output to be different than beta. You don't want you get a ciphertext. I want this to be different than beta. That's what I want. I don't want like underneath the hood to be something that's different than beta. So this seems like a bad idea. Like it gets us nowhere. Yes, again, where are we? We said if we knew trapdoor, we would be done. The hash function, the eval of the hash function will take this trapdoor, compute beta, and output not beta. You know, move it by one, move one of the bits by one, whatever, as long as it's not the beta. And now they say, no, let's do everything under the hood. What? Then we'll get an encryption. Why would that not be beta? Like, it seems like you're not getting anywhere. To me, it seemed like when they first presented this idea, I'm like, okay, this seems completely useless. So what? Now everything is under the hood. And guess what? We're almost done. Yeah.
Can we somehow like find the randomness that gets us the encryption of this knowledge?
You take the randomness.
To find the randomness so that encryption of B-byte was 1 gets us that one.
So you know what? I want to say something even before that. There's even a mismatch. Beta, let's say, consists of lambda bits. For example, in our case, because we repeated, it's lambda bits. This is not even lambda bits. It's much more than lambda bits because we encrypt bit by bit. It's much bigger. It doesn't even. It's like seems like completely bogus. This is going to be the length of beta times security parameter. So it's not. It doesn't even correspond to. Like the sizes don't even match. So it seems like an encryption is not helpful. Yeah?
How do you compute beta bad given alpha in the trapdoor?
Oh, good. The only way he can compute beta bad is if he has the... how can you compute given the trapdoor, you're saying?
Yeah.
Okay.
Yeah.
So what he will do, the trapdoor in this protocol allows you to kind of open the commitment. Okay, so now you see each point if it has a 0, 1, 0, 1, 0, 1. So now, why do you know what's beta bad? Because now you look. If it has just a Hamiltonian cycle, I mean, the truth is it's easier to see it if you have the pi. Suppose you always also committed to pi, right? It's just easier to see it that way. Suppose I tell you don't only commit to that, commit also to your pi. Now, you see what's in there. Either if you remove pi, you see what if you so you see if so you look at all the edges of pi of g, and you make sure that these edges are 0. Everywhere they're 0. If one of them is 1, you know that he won't succeed in open, and then this is not bad. Then the b equals 1 is not bad because here he will fail. The bad is where he will succeed. A bad b is the b that. Like a bad beta is the beta that will allow him to succeed. So now if you can open everything, now you can see. If there's one edge of pi of g, if there's a non-edge that has a 1, then you know, okay, this is definitely not bad. He can, and so he won't be able to see, so this is the beta bad. On the other hand, if all the non-edges are indeed 0, you know he can't open the Hamiltonian cycle because there is no Hamiltonian cycle. So then this becomes the bad. So if you know what's in the commitment, you can tell which one is the bad. So the trapdoor allows you to compute the bad efficiently. That's the point. Yeah?
So does that mean the trapdoor is the random coins used in each call to ANK?
The random coins used?
Like the randomness that's used inside each ANK. Like, is that what the trapdoor is?
No. I'm thinking of the trapdoor as being the secret key corresponding to the public key. So I'll tell you the problem of using the randomness, then it's chosen by the cheating prover. And I don't know how he's going to use it. I don't want to, the trapdoor, you write the trapdoor, okay, this is an important point. So note, I can open this commitment by giving you the randomness that I used to generate this commitment. That'll be a good trapdoor. But when I designed the Fiat-Shamir hash function, I have no idea what randomness the cheating prover is going to use. Maybe it's even deterministic. I don't know what he's doing. He may just give me a bunch, I don't know. So I don't know ahead of time his random coins, and different cheating provers will have different random coins. So I want to put something in the CRS, the hash function, the Fiat-Shamir hash function. So this trapdoor is actually going to be the secret key corresponding to the public key. The secret key is not going to be used in here. It's never going to be used in the protocol. But it will be used in the analysis. Okay? Great. Yes?
Is this only limited to interactive proof where you commit to the witness, or can you generalize to where the first message is not necessarily the witness?
Again, you're saying is
Only limited to proof system where you commit to the witness, or can you generalize to proof system where the first message is not necessarily the witness?
so okay. So this technique works. Okay, so this technique works for this protocol where you commit to something in open. And after I'll show you why, I'll show you that it's actually more general, and it applies to a large, actually, slew of protocols where there's no commitment whatsoever. For example, it applies to GKR protocol, where it's just sum check. It applies to the sum check protocol. And so it's not specific to this. And I'll show you later, all you need is kind of this trapdoor that tells you where the bad kind of challenges are. And once you have a trapdoor that tells you where the bad challenges are, then you kind of can use it. But we'll mention that at the end of class, like towards the end. But yeah, we'll see that it's general. So in some sense, you don't even need to look too detailed into that protocol. The idea here is more high level. We say, look, in any interactive proof, there's the beta that are bad, like bad for security, that are good for the adversary. But they're bad for security. If the adversary managed to hit a bad beta, an alpha for which h of alpha gives him a bad beta, then he can cheat me. I want to avoid these bad betas. And now we're saying, suppose there's only one bad beta, for simplicity. This one has one bad beta, so we're good. If it has one bad beta, I want to avoid that one. Now, if there's some trapdoor that allows me to compute that bad beta, then I can't put that trapdoor in the kind of the hash function and give it to the world. There's a reason why it's a trapdoor and not public. Here, in this case, it's for zero knowledge. But what I can do is give an encryption of the trapdoor. And actually, in the actual scheme, it won't be encryption of that trapdoor. It's going to be encryption of zero. Nobody's going to ever decrypt this thing. But let's think of it as an encryption of the trapdoor for now. Now, again, where are we? Why did we make any progress here? Okay, so next is the most amazing point, I think. When I saw this, it took me a very long time to process because it's such an ingenious idea. But here's the idea, okay? So they say, yeah, you know what? I'm going to take nevertheless, my hash function is going to, so then they say, okay, you're right. This kind of hash function that has the trapdoor in it, and you evaluate the trapdoor, you're right, it's not good. It doesn't even type check. The output is not the length it's supposed to be. Yeah, this is nonsense. Let us fix this. And here's how they fix it. Let me put the eval here, because it'd be nice to see. So here's their fix. They said, you know what, fine. That may have been the wrong function. We're going to encrypt. So our hash key is going to consist of encryption of another function, G. I'm using, by the way, I'm using the hat to denote fully homomorphic encryption as opposed to standard encryption, okay? That's often we use in the literature. The hat is kind of a shortcut to denote public key comma encryption of G. And when you use this hat, we usually use it when we want to talk about fully homomorphic encryption, okay? Okay, so now they say, okay, this is going to be nevertheless, I'm going to encrypt a G. What's the G? We'll see. I'm going to encrypt a G, and here's their hash key. The hash key is going to be, I'm going to generate a public key and encrypt a function G. Okay, so it's like the public key corresponding to G, and then G, which is just another shortcut to say encryption of G. And when I say I encrypt a G, just think about encryption, the description of the circuit. Okay, so there's some way to describe the circuit. I encrypt the description. Okay, so I encrypt this description of a circuit G. What this G is, we'll see. Okay, but that's my hash key. So this is the hash key. How do you evaluate hash key and alpha? They say, you know what? Just compute G of alpha under the hood. How do you compute G of alpha under the hood? Essentially, they say, do the eval of the FHE. There's two evals, so it's a bit confusing because we usually denote the evaluation computing the hash function by eval, but now we also have the eval of the fully homomorphic encryption scheme. So take the fully homomorphic encryption scheme, take this ciphertext G, so take the public key corresponding to the ciphertext. What's the function? What's the circuit C? It's going to be kind of a universal circuit sub alpha. I'll tell you what this is in a second. And the ciphertext is G. And this universal circuit sub alpha, all it does, the definition, it takes as input a circuit G, and it outputs G of alpha. So essentially what we do, what this hash function does, is exactly what we said before. It takes an encryption of G. How does it relate to the trapdoor? I'll tell you in a second. Before we said G is just kind of it just has the trapdoor in it. And before we said G is just this G. Computes bad and it has the trapdoor, and we encrypt G. Now they say, okay, you're right, there's a problem. We'll tell you what G is in a second. But same idea. We encrypt this G. Maybe it'll be a little different, but we encrypt G, and the hash function computes G and alpha under the hood. So it takes the original first message alpha and computes the function G under the hood. I'm like, we just went over it. It doesn't work. Well, then you get the encryption. It doesn't even type check. Blah, blah, blah. What? So here's their idea. Okay, now this is the most beautiful part of today's lecture. Okay, so they say, okay, so think of this, let me just write it short, kind of hand wave. This is going to be G of alpha encrypted, right? Because this is what U does. U does, it computes G of alpha. So what you get back is an encryption of G of alpha. Now they say, okay, and by the way, in their scheme, let me first say, in their scheme, what is G? It doesn't matter because it's encrypted. It's the all-zero circuit of a certain size. So in their scheme, this G is going to be the all-zero circuit of size like T zeros. What T is, we'll see in a second. Okay, but that's all it is. That's the hash. This is the Fiat-Shamir hash function. The question is, why is it secure? Because it seems like there's no way this works. But let me just say again, their Fiat-Shamir hash function, what does it do? It generates a public key. It encrypts, in the actual scheme, the all-zero string, to 000 up to T times. We'll see what T is in a second. In the analysis, we're going to play with this G. But this is what it is. And when you give him alpha, it computes this circuit, which is the all-zero circuit, under the hood. That's all it does. And that's the B. That's going to be the beta. You should be very confused, but I'll explain. Yeah.
How does the all-zero circuit work?
Just think the zero. Everything is, I don't know, whatever. It doesn't matter. All pluses, all plus gates, or it actually doesn't matter because nobody's going to ever decrypt it. So I guess I'm saying each circuit you can describe it with kind of bit 0, 1, 0, 1, 0, 1 in some way, you know. So put all 0 bits. So I don't know if it even describes the circuit. Yeah, Anand.
Could you just use the original like beta bad plus 1 hash thingy by it has the prover has some circuit that computes gamma as a function of beta. So just do that under the FHE and get an encryption of gamma. Or does this not work for some reason?
No, I'll tell you why it doesn't work. Okay, good. No, great question. So the question was the following. You're saying, you know what, change the protocol altogether. You then change this protocol and ask the guy, you don't need to be, blinded to this Fiat-Shamir paradigm. Change it a little bit. And now you put a encryption of the trapdoor. Tell this guy, so now he computes beta under the hood. Tell him to compute gamma also under the hood. And then we don't have a problem. The problem is that he can cheat. Why? Because when he answers gamma, he knows the trapdoor. But actually, 1 second. You're right. Under the hood, he knows the trapdoor. Yeah. So, hold on. Yeah, the problem is that under the hood, he knows the trapdoor. However, I'm not sure actually that that's a problem. because at that point, let me think for a second. I think it actually may work. Okay, so look, it changes the protocol. For example, now it's no longer publicly verifiable because you need to, now his message is encrypted. So you need to decrypt in order to learn it. So there are issues with these, but also I'll tell you more than that. If indeed you put in the Fiat-Shamir, in the actual scheme, you should think of it, the people who generate Fiat-Shamir, they actually don't know the trapdoor. They don't know the trapdoor. There's a scheme and it's sound, and there is a trapdoor, but nobody knows it. And the people, they don't actually know the trapdoor. So in the actual scheme, there won't be an encryption of the trapdoor. It's in kind of, the idea is we'll say, well, in the actual scheme, you don't use the trapdoor. But it's indistinguishable. You don't know if you encrypted 0 or encrypted the trapdoor. So we're going to prove soundness, assuming you encrypt the trapdoor. But in the scheme, you won't encrypt the trapdoor. So then in the scheme, the gamma is going to be useless, kind of, because it won't correspond. Yeah? Okay, great. So, okay, great questions. So where are we? So we said, here's the Fiat-Shamir hash function. The Fiat-Shamir hash function will take actually an arbitrary G of a certain size. It doesn't matter, because nobody's going to decrypt that ciphertext anyway. And all it will do is a computation under the hood. And now it seems like, I don't know, it seems like that cannot work. Nevertheless, I'm going to prove security in like 2 lines. It's okay. And the proof is like ingenious, really. This construction is it's very tempting to try. It just doesn't work. When you look at it, it's like, okay, and then what? And then what? But here's their idea. Their idea is following. Look, all we need to argue is that for every alpha, G of alpha is not beta bad. That's all we need. So then in the analysis, I'm going to say, so again, this is the actual hash function. You have an encryption here of G. What G, this G is, I don't care. It's like the fixed circuit, whatever circuit you want to put, and nobody's going to decrypt it. In the analysis, I'm going to say, you know what? I'm going to replace this G with a very special G, with the G whose encryption is not beta bad. But you're like, which G hat? Which G hat? How do we construct a G so that we know that encryption of G on alpha is not beta? Yeah?
Just a syntactic question. What does this notation mean? Like, is it like an encryption of G? Like, is the hat over the whole thing?
Yeah, sorry, yeah. Sorry. This is a encryption with public key of G alpha.
Yeah.
Yes, sorry. Thanks. Thank you. So any idea what, okay, I'll tell you won't believe me, but I'll tell you anyway. It's math, so of course you'll believe, but you'll be mind-boggled for a while. So here's their idea. Their idea is they say, okay, here's my G. I need to ensure that you're not beta, so I'm going to make my G be the decryption secret key of beta, and I'm just going to add like the 1 to it, so I know you're not, like, I guess I'll write XOR because we're over 0, 1. I'll XOR with this with 1. That's my G in the analysis. So in the analysis, I'm going to say, suppose you succeed in breaking the Fiat-Shamir, you're also going to succeed with this G, because it's encrypted. You don't know the difference. You have no idea what's underneath the ciphertext, underneath the encryption, so you should also succeed in breaking with this G. Now, this G looks bizarre because I'm decrypting. This is not a ciphertext. This is just a bunch of strings, like a 0, 1 string. It's a random string. It's not a ciphertext. What does it mean to decrypt this thing? It's like, this makes no sense. However, but if the length of this is take a ciphertext that the length is like these lambda bits. So you can, look, this is a function, so you can compute this function, not on a ciphertext, but compute this function. Okay, so I decrypt the beta message, which is not even a ciphertext, and I add 1. I XOR it with 1. I XOR it with anything that's not 0, just to move it from the bad. Now I want to argue. Now we know that encryption of this cannot be beta. Why? Now I can argue this. Why? Because if it was equal, if you decrypt this, then you'll get a decryption of this. If you have 2 strings and they're equal, if you decrypt one, you can apply decryption for both, they'll still be equal. The decryption is just a deterministic function. So I guess if I want to argue now for this G, I want to argue that this, which is the Fiat-Shamir hash function on alpha, this is the Fiat-Shamir hash function on alpha. I want to argue this if. I want to argue if it was beta, I'm going to get a contradiction. I want to argue it's not beta. Why? If it was, then I can apply decryption on both sides. Then it means that decryption of this will be equal to decryption of this. Of course. Okay, what is decryption of this? G alpha. So I just decrypt the encryption of G alpha, I get back G alpha. But I know G alpha is not the decryption of bad alpha, because G alpha is the decryption of alpha, not plus 1. So it can't be. So again, in the analysis, so let me maybe write this a bit formally. So let me write it up there. I'll use this part. So here's the actual proof of soundness. So suppose, there's one thing I glossed over fast. Okay, we'll go over it in the analysis, we'll see it. So I say, suppose there exists poly-size cheating prover, and he fixes some graph G does not have a Hamiltonian cycle, and cheats. And successfully cheats with probability, big, let's say greater than epsilon. Epsilon is not negligible. Then I'm going to say, then I want to argue, then it means that P star also succeeds with probability, I said close to, epsilon may be minus negligible, but similar probability. If I change the hash key, before the hash key was public key and some encryption of some bogus G. Now I say it will also succeed if I take public key and this specific G. Let me call this G star. Okay, so that's the G in the analysis. So again, how does the analysis go? I say, suppose there exists a cheating prover that takes a false statement and succeeds in proving nevertheless, in convincing. Then I want to say that he will also succeed if instead of giving will also succeed with hash key, which is public key and encryption of G star, of this G star. Why? By semantic security. Okay, because you can't distinguish between encryption of G star and encryption of G. Yeah?
So here we're using the proof is efficient.
We're using the fact that the proof is efficient.
So computational soundness now.
Computational soundness, yes. We're using the fact that the poly size, he's efficient, and therefore he cannot break semantic security. So he cannot distinguish between G, whatever the bogus G that we put in the CRS form, the all-zero circuit or whatever, and this G star. I cheated slightly here, but let me move on. And we'll go to the cheat in a second. Okay, but let's say you believe that, even though you shouldn't, but it's very delicate, so we'll go there. But okay, semantic security. Now I'm saying with this G star, now information theoretically cannot cheat. He's stuck because guess what? Forever, you're saying he produces alpha, beta, gamma accepting. Right? That's what he means he cheated. So it means that he got alpha so that H of alpha is bad. Because you can only cheat with a bad alpha. That's the definition of a bad beta. That's the definition of a bad beta, one that you can cheat with. So he found an alpha so that H of alpha is bad. But this G star never hits bad. That's how we made it. It's so that G of alpha is never the bad alpha. Yeah?
Doesn't G star depend on the key?
Ah, that's what I glossed over, exactly. Good, good, good. So that's the proof. However, there is a cheat. And the cheat is, look, G star, to compute G star, I said just describe G star. Like when I mean encrypt G star, I mean give the description, like encrypt the description of G star. Okay, so let's recall what does G star do. G star decrypts. So you need to know the secret key corresponding to public key. We said that like you can encrypt, semantic security holds that for any fixed messages, M0 and M1, you cannot distinguish between, is it here? Yeah. For any fixed M0 and M1, you cannot distinguish between encryption of M0 and encryption of M1. But here I'm saying you cannot distinguish between encryption of the secret key and encryption of, let's say, other bits. That's a different story. And indeed, we assume what's called circular secure FHE. So we assume not only that we assume that you cannot distinguish between encryption of the secret key and encryption of the all zeros. That's an assumption. Do you have a question? Yeah.
So far, it seems like B beta bar is also given, not computed. Like, how do we extract?
Oh, no, it's computed. Sorry. Okay, good. No, what I meant here, okay, thank you very much for the question. Here's what G star alpha does. G star of alpha, it has actually, let me write more carefully. It has trapdoor and secret key hardwire. The first thing it does, it computes bad alpha using trapdoor. This is kind of corresponding to our scheme. Then he takes what he got, the bad alpha, he decrypts it using the secret key. Then he XORs 1 to the least significant bit or something like that. So yeah, it does compute it. Yeah, so this G star, you need to encrypt trapdoor and you need to encrypt secret key. Now, encrypting the trapdoor is not a problem. It has nothing to do with the key. But the problem is you also need to encrypt the secret key corresponding to the public key. But yeah, thank you for the question. That's a great question. So, if I want to repeat, G star alpha, what does it do? It takes alpha, it first computes the bad beta corresponding to the alpha using the trapdoor. Then he takes the string, he decrypts this weird string using the secret key, and then he XORs it with, XORs the least significant bit with 1, or any bit with 1, just to make it not equal.
Is it still the secret key?
It's the secret key corresponding to this commitment. That's why I said, this trapdoor in some sense is also a secret key of public key encryption. But there's two encryption going on. One is the FHE encryption. And one is how we implement this commitment. So you're right that we implement this commitment also with an encryption scheme, but it's better to kind of forget it because otherwise it's confusing that there's two encryption schemes. So here I want to say, suppose you have a commitment and there's a trapdoor that allows you to open it. Forget that this trapdoor is also a secret key. So now I'm saying you need this trapdoor to open the commitment, which you're right, this trapdoor happens also to be some a secret key because that's how we implemented the commitment. And it has the secret key corresponding to this same public key. You see, so I guess what's the problematic part is that the hash key consists of a public key of a fully homomorphic encryption scheme. And to describe G star, you need the trapdoor, which is not a problem. You could just encrypt this trapdoor under public key. It's a fresh public key. You can encrypt any. This is kind of fixed compared to this public key. But you also need to encrypt the secret key corresponding to this public key. And for that, we need to rely on circular security. So let me just quickly write what I mean by circular security, and then we'll break. So I'll write it here. It just means that public key and encryption of the secret key is indistinguishable from public key and encryption of, let's say, the all zeros. And let me just mention the secret key here, you can think of it as lambda bits, let's say, security parameter number of bits. Then when, if we think of bit-wise encryption, this is encryption of, it's like encryption of secret key, the first bit of secret key encryption, the second bit, it's like lambda encryptions. And this also, I mean encryption of zero, encryption of zero, encryption of zero. We do everything bit by bit. And the assumption is that you have an FHE scheme so that you cannot distinguish between whether the lambda encryptions, each one bit encrypts a bit, whether these encryptions are all zero or whether they correspond to the bits of the secret key. So that's an assumption. By the way, we know, so the question is, well, do we have FHE that have circular security, question mark? Well, we do under an assumption it's called circular secure learning with error. So we just move this kind of circular secure into the assumption. We believe this assumption to be true. We don't know, but actually we can remove all this. We actually don't, it turns out we don't need to put the secret key there. And there's a follow-up work that kind of did more work, a lot of lattice work. So you need to kind of really, here I didn't talk at all about lattice. I mean, as long as you have fully homomorphic encryption that's circular secure, we're all set. I don't care what this is like. But then there's follow-up work that looks at the specific kind of fully homomorphic encryption scheme based on lattices and does a bunch of lattice tricks to remove the need for circular security. So this is something I didn't show you, but there's a follow-up work that does that. Okay, so I want to take a break, but if before a break, are there any questions? Yeah.
So here the size of the circuit key has to be large enough to contain this specific
Good,
example.
exactly. So good question. Very good question. Guys, you're really having fantastic questions today. Thank you. So going back, what is this T? This T is the number of bits needed to represent this G star. Because in the analysis, I convert the 0 to the T with G star, with the description of G star. So this is exactly what T is in the analysis. Any further questions? Okay, so let's take like maybe, I don't know, 8-minute break. Feel it was intense. Takes like 8-minute break or so. And when we'll go back, we'll do the NIZIC.